Good morning, class, and welcome to this video on Momentum 5 collisions. Okay, today we will be able to define elastic and inelastic collisions and determine what equations to use for each situation. Okay, so we're going to have collisions. So that means two things are colliding, and we're going to be able to talk about an elastic collision and an inelastic collision. So let's first define these two. Elastic. Kinetic energy is conserved in collision, and inelastic, kinetic energy is not conserved. Kinetic energy is not conserved. Some is transformed. Some is transformed into other forms, into other forms of energy. That could be potential energy. That can be it could be gravitational potential energy. It could be elastic potential energy for a spring. So these are our two definitions. Kinetic energy is conserved. Kinetic energy is not conserved. Okay. Now I know that you look at that and that makes no sense to you whatsoever. So I'm going to make a chart on the next page and start drawing some pictures as well, and let's take a look at that and see if we can start putting two together. So let's make a nice little chart here. So we're going to have elastic collisions, and we're going to have inelastic collisions. Okay, so here we go. In an elastic collision, momentum is conserved. Okay, momentum is conserved. Okay, that means the final momentum will equal the initial momentum. Okay, in an inelastic collision, momentum is also conserved. Okay, momentum is conserved no matter what. Momentum final equals momentum initial. Okay, so for both of these equations, or for both of these situations, we're going to use our m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Okay, this is our equation. We use this for both situations. Okay, so that is momentum. Now, let's talk about energy. Okay, energy. In an elastic collision, energy is conserved, meaning the final energy equals the initial energy. Okay, in an inelastic collision, energy is conserved, meaning the final energy equals the initial energy. Okay, so for both situations, we can go back to our original equation that we learned before, mgh final plus 1/2 mv squared final, v squared final, plus 1/2 kx squared final equals mgh initial plus 1/2 mv initial squared plus 1/2 kx initial squared. So this equation can apply to both situations. Okay, so we have a collision, and so far nothing has changed. Nothing has changed. Now here's where we get to the difference. Okay, in an elastic collision, kinetic energy is conserved. In an inelastic collision, kinetic energy is not conserved. Kinetic energy is not conserved. So in an elastic collision, we can take this equation right here. This equation can come down here, and it's simply going to be 1/2 mv initial squared. Excuse me. Let's erase that. One half mv initial squared equals 1/2 mv final squared. Excuse me. I need to add one thing here. Total kinetic energy is conserved. So this could be two objects. So this might look also like this: 1/2 mv1 m1 v1 squared plus 1 half m2 v2 squared, and that's going to equal, I'm going to write it down here, 1 half m1 v1 final squared plus 1 half m2 v2 final squared. So if there's two objects with two different velocities, we have to separate m1 from v1, initial, final, final, and so this is going to be the total kinetic energy is conserved. Okay? On this one, kinetic energy is not conserved, but energy is conserved, so simply this equation right here goes right here. Okay, so we're going to use this equation right here. All right? So let's draw a picture of this. Let's draw a picture with this. Let's go to the next page. Let's draw a picture of elastic and inelastic. In an elastic collision, I'm going to use billiards. Billiards. Come on. Billiards or pool as my example. So we have a billiard ball coming at another billiard ball. Okay, coming at the 8 ball. This billiard ball has a velocity. It has an initial velocity. This one velocity is 0. Okay? They collide. They collide here, okay? So collision. It's very violent. And afterwards, this billiard ball has a velocity of 0. We'll say, for example, and the 8 ball V final equals V initial. So this is a perfect collision. It is a perfect collision where all of the velocity is transferred to the 8 ball. So momentum is conserved, energy is conserved. This ball, these two weigh the same amount. So M1 and M2, those are equal. And so this means momentum and energy are, and kinetic energy are the same for both. Momentum and kinetic energy are the same for both situations. The cue ball transferred all of its energy, all of its momentum to the 8 ball. It was a perfectly elastic collision. No energy was lost. No energy was lost in this situation. Or it could also have been where they collided and the cue ball is now moving this direction and the 8 ball is moving in this direction. So maybe they're both moving. However, the total kinetic energy and momentum is still the same, okay? So if we did 1 half mv squared here and we did 1 half mv squared here, it would equal 1 half mv squared of this one right here. No energy right here. No energy is lost. No energy was lost. All energy was converted into movement. All momentum was converted. In an inelastic, and I'm going to make this a completely inelastic. Completely inelastic. In a completely inelastic situation, both objects stick to each other. So a very common example of this would be like a bullet hitting a block of wood. They collide, and afterwards the block of wood and the bullet are stuck together. Okay? They are stuck together. In an elastic collision over here, two objects, they collide, and energy Energy and momentum is transferred from one object to the other. Okay, energy and momentum is transferred from one object to the other. In this one, energy is not transferred. Energy is, the blocks gains energy and momentum, but there's not a collision where they separate. They are completely stuck together. So both objects stick to each other. This picture in your book is a great picture. Excuse me. This picture in your book. It just shows an elastic collision between the ball and the surface. If there was no energy lost, so this is no energy lost, then this means the ball would bounce and go to the same height every single time because no energy is lost in this process. There's no friction, there's no heat change, there's nothing. This ball will completely gain all of its energy back after the collision. In an inelastic collision like a basketball, it's going to lose some energy. It's going to lose some energy. This is reality. This is reality, okay? This is, there's no such thing as completely elastic. But we talk about these it's basically to simplify our math a little bit. It's to simplify our math so you can get the concept, okay? Because we do have situations that are very close. But in reality, if this same ball dropped, it's going to lose some energy to heat. It's going to lose energy to heat and friction, which might be the same thing sometimes. And so some energy is going to be lost. So this thing dropped, it hit, some energy was lost in the process, okay? And a completely inelastic collision there would be no separation. It just stops. So those are our two situations of elastic and inelastic. So what does that mean for you? Well, if we have an elastic equation, if we have an elastic situation, we need to be using this equation here and this equation down here. If we have an inelastic situation, we need to be using this equation here and this one down here and this one right here. So now you know what equations you need to use, and the next couple of videos are going to be us doing some examples.